In this lesson, we will define free energy and describe the meaning of spontaneous reactions in terms of enthalpy and entropy changes. And we will also learn to determine the spontaneity of a reaction based on the value of its change in free energy at both high and low temperatures. Gibbs free energy is the energy available in a system to do work, and this allows us to predict the spontaneity of a reaction. When delta G is greater than 0, the reaction is non-spontaneous. When delta G is less than 0, the reaction is spontaneous. Early work tried to relate spontaneity to either enthalpy or entropy, and while they found that it worked many times, it didn't work all the time. And so delta G is actually a mathematical expression that accounts for both the entropy and enthalpy of a reaction to predict whether it will happen spontaneously. One question students often have is, what do we mean by spontaneous? And what we're saying is that this occurs without any input from external systems. For example, if I take an ice cube at 40 degrees Celsius, it will spontaneously melt. I'm not having to do anything to it, it will just melt at 40 degrees Celsius. If I took that same ice cube at minus 10 degrees Celsius, it would not melt, and so that would be a non-spontaneous process. Another example of a spontaneous process is a ball rolling down the hill. If you place the ball at the top of a hill, it will roll down. You don't have to push it or give it any start, it will just go down the hill. When we look at chemical reactions, we can look at them in the same way. For example, the reaction of carbon monoxide plus oxygen to yield CO2. The delta G, or the Gibbs free energy value, is minus 81 kilojoules, which means this reaction will happen spontaneously. Delta G, or Gibbs free energy, is a mathematical expression which equals delta H, the change in enthalpy, minus T, the temperature in units of Kelvin, delta S, or the change in entropy. So delta G equals delta H minus T delta S. And it's the relative value and signs of these two values, of the delta H and delta S, which will determine whether delta G will be a positive or a negative value, and therefore be non-spontaneous or spontaneous. Another expression we often use when looking at reactions is favorability. When we look at the value of the enthalpy of a reaction, it will tell us something about the favorability of a reaction. For example, if delta H is greater than 0, we would say that is endothermic, and that is an unfavorable reaction. For delta H less than 0, it's exothermic, and so that contributes to the favorability of a reaction. And this is because that a delta H less than 0 is more likely to be favorable and more likely to be part of a spontaneous reaction than when delta H is greater than 0. For entropy, delta S greater than 0 means the increasing entropy, and that is a favorable process which contributes to the overall spontaneity or favorability of a reaction. When delta S is less than 0, we are decreasing the entropy, and that is unfavorable. Nature tends to go towards an increase in entropy. When delta G is greater than 0, this is a non-spontaneous reaction, and it's considered to be unfavorable. Delta G less than 0 is spontaneous and would be considered a favorable process or reaction. While we will focus on more of a qualitative assessment of whether something is spontaneous or not and looking at the relative signs, I am going to do one calculation as an example to show you how the different values affect the overall spontaneity and the overall delta G value of a reaction. Let's look at the reaction between nitrogen and hydrogen to form ammonia. We see that delta H equals minus 92 kilojoules, delta S equals minus 199 joules per Kelvin, and our temperature is 25 degrees Celsius. We have our equation delta G equals delta H minus T delta S, and we can plug in the values we know. So delta G equals minus 92 kilojoules minus 298 Kelvin, because we have to convert to Kelvin because our units of delta S, and then we have minus 0.199 kilojoules per Kelvin. Note that I had to convert the entropy value into kilojoules. When we solve this, we get delta G equals minus 33 kilojoules, which indicates a spontaneous process. Let's go through what happens when we're dealing with positive and negative values of delta H and delta S. First, let's look at an example when delta H is positive and delta S is negative. Remember that temperature is in units of Kelvin, therefore the value will always be positive. If I have a negative delta S value, then my minus T delta S value will be positive because a minus a negative value will be positive. So my first term, the delta H, is positive and the minus T delta S term is positive. As a result, our delta G value will also be positive, and this indicates a non-spontaneous reaction. Now we will look at the opposite signs when delta H is negative and delta S is positive. For a delta S being positive, minus T delta S will be a negative value. So if both terms, the delta H and minus T delta S, are both negative, we will have a negative delta G value, and a negative delta G value indicates a spontaneous reaction. The next two are a little bit trickier. When we have both signs that are negative or both signs that are positive, we then have to look at the value of the temperature. So if delta H is negative and delta S is negative, then the minus T delta S term will be positive. Now we have a negative term and a positive term, and it is the magnitude or the size of those numbers that will determine whether or not we are dealing with a spontaneous or non-spontaneous reaction. At a low temperature, the second term will have a very small magnitude, and as a result, the delta H will have a greater magnitude and will be the dominant term, and as a result, we will have a negative delta G value. At high temperature, we will have a dominant second term because when T is large, the T delta S term will be large, and it can be larger than the delta H, so the positive term will predominate, and as a result, we will have a positive delta G value and a non-spontaneous reaction. Low T will give a negative delta G and a spontaneous process. So going through, we have a delta H that is less than 0, a minus T delta S term that is greater than 0, and so the delta G will be dependent on the magnitude of those values. The bigger the delta H, smaller T delta S will result in a delta G that's less than 0. The opposite will be true for a high temperature. The T delta S term will be larger and the delta H term will be smaller, so we will get a positive delta G, and this indicates a non-spontaneous process. When we talk about high T and low T, we aren't worried about specific values, and that's as far as we'll go. You would never have to decide if a particular temperature is a high temperature or a low temperature. The next scenario is if delta H is positive and delta S is also positive. When delta S is positive, the minus T delta S term is negative, and we will still look at this in terms of low temperature and high temperature. So at low temperature, the second term, the minus T delta S, will have a small magnitude, and the delta H term will have a much larger magnitude, and so we will end up with a positive delta G value and a non-spontaneous process. If we have a high T, the T delta S term will have a large magnitude or a high value, and it will be greater than the magnitude of the delta H term, so the negative T delta S term will as a result predominate the value of delta G, so we will get a negative delta G, which will be a spontaneous reaction. I encourage you to go through and understand how we got the different signs rather than trying to memorize the table, so that you can understand the contribution of both delta H and delta S to the overall spontaneity of a reaction.